Okay, this is the second video of chapter 1. In the previous video, I described how we can define a probability, and I told you that repetition of an experiment is the key to define a probability. Okay, that is understood. That is not that difficult to understand. But the problem is, so far we only considered a coin toss. So it's too simple. But we have to extend our view to more realistic data, actual data. So I will show you an example. Survey. So many of the data we are going to use in economics, is survey. So that means survey is a way to generate data. So it is a random experiment. But where does the randomness come from? Well, I'm going to describe that. So the randomness is coming from when you choose a person, right? You randomly choose individuals, or you randomly choose a firm, you randomly choose a date. Like, it depends on how you design a survey. But so for example, like every 10 years, like the United States does a census. But it is not actually not a sample, because that is the population. It obtains information from everyone. So we don't, it is not statistics, it's just computation, right? If you have the census data, you don't miss, assuming that you don't miss anyone, and you really meet every single person in the United States, then you don't need to do any inference. You know the answer. The truth is in the census data. So that is purely computation, not statistical inference. But that is not, by the way, that is very, very costly, and you cannot ask everything in the census data, right? So depending on the purpose of your analysis, there are some surveys. Like here, I'll show you some examples. Panel study of income dynamics. If you would like to understand income dynamics, then you design questions more specifically toward that, and like choose people. And current population survey. This is kind of a smaller version of census. And national longitudinal survey of youth. To understand how the growth of children, there is survey data. And health and retirement survey, as you can see, about health and retirement. Consumer expenditure, survey. And consumer finances. So all of these are surveys because you cannot ask everyone. Instead, still you can ask like a large number of people, like say several thousands, several 10,000, right? That's a huge number, and still that costs a lot. And what you have to be careful is you have to choose them randomly, right? You cannot just ask your friend. You have to choose the survey respondents randomly. That requires advanced statistical techniques, and then from there it's survey, right? So give them a questionnaire and collect their answers. That's the observation. So in this process, this survey is an experiment, and the randomness is coming from randomly choosing a person. That's the main point. Then in that sense, then to see every person in the United States, to ask the same question to every person in the United States, in theory you have to do it infinite number of times. Anyhow, you are not going to get there, so we just assume that you need infinite number of choosing a random person. Then you can get to the population. But anyhow, in practice, you cannot observe everyone. You are just observing some part of the population based on randomization. So the point is randomness. Okay, so what we just defined for the probability applies to our data, many of our data. So this is okay. This is easy to understand. But what is more annoying is, weird is time series data. So for example, think about the sentence like the probability of rain on Labor Day is 30%. So say maybe you are going to watch this video on Labor Day. I don't know if it rains or not, but anyhow, suppose that it's 30%. This sentence is okay. It's a complete sentence. You know what it means. But the problem here is, what is the experiment here? When you define probability 30%, you have to repeat. But how can you do that? That is, so we use some trick. So it's you may not agree with that, but we think of a hypothetical experiment like this. So we have a lot of possible weather scenarios. Like you observe, like, temperatures, pressures, and where clouds are, how fast winds are, wind blows. Given those possible weather scenarios, like given the situation, there are different scenarios. How clouds move, things like that. And we in our mind, like tossing a coin or throwing a dice, Mother Nature, someone chooses one possible scenarios for Labor Day, given the situation. So we will assume that the experiment is repeated every year on Labor Day. So considering, assuming that every year the Labor Day has similar temperature and similar weather situations, then we observe one outcome every year. The experiment is in here. The Mother Nature, someone chooses the realization. So I understand if you think it's absurd, but it's not my fault. This is the standard view on the probability. Because we have to define probability here, then it is natural to think about an experiment. If you have agreed what I have explained up to this point, then you have to follow this, right? So that means if you agree with this experiment, then our observations from the past is data. That's simple, right? Then we can apply the same structure of probability in this data. This is time series data. So time series data analysis is actually pretty different, more difficult. That is not my expertise. So because I know it's more difficult, so I did not spend much time on studying that. But it's important. A lot of many important questions, especially in macro and finance variables, are based on time series observations, like GDP, stock returns, right? So when you analyze the stock market, we usually base our opinion on the past performance. Like say, the reason why I buy Apple stock is because Apple does really great things in the past decade, so I believe it will keep going up. So okay, then that is the maybe most scientific, most reasonable judgment in stock market. Then you are assuming that the experiment is repeated over time. What you observe in the past is just realization of many possible outcomes, right? Okay, so up to here we learned the basic components of probability structure, and I described how to apply this structure to real data, survey data, time series data. These are two typical data structures in economics. Oh, and by the way, one disclaimer. What I explained, as I said, you may think it's absurd. That is true. And true, actually, there are different approaches in statistics to probability. The most famous alternative is Bayesian approach. So Bayesian statisticians do not agree with what I explained. So they use different framework. However, like what I explained is based on a frequentist approach. That is the majority. That's why I'm explaining that. And it is just an introduction course, introductory statistics. So I don't think I need to explain other approaches because that's more philosophical, right? We don't know what is like. It's about definition of probability, so it's less important at this time. So if you are more interested, then maybe you need to go to like graduate programs, or you can take Bayesian statistics course if available. Okay. Okay, now I'm going to think about data and probability, how to connect them. So, think about now, I'm going to think about repetition of experiments. Like here, I think of rolling a dice 200 times. So you repeat the experiment 200 times. And I record the outcomes. Like 1, 5, 4, 4. So each time up to 200, I observe these kind of numbers as an example. This table contains all the information. That is the data, right? But as you can see, I cannot show all 200 observations on this slide. It will take, I don't know, at least like 5 or 6 slides if I were to show you all the observations. That means it is not an efficient way to present the data. We need summary. We need to summarize the data. So that's this one. Frequency distribution table. Instead of showing all the 200 observations, what you can show is just a count of each outcome. Say, out of 200, result 1, outcome 1 happened 33 times. Outcome 2 happened 31 times. Like that. So, 4 happened a lot. 5 did not happen that much. Of course, some of the frequencies, some of the counts of each outcome must be the total observations, number of total observations, which is a sample size, right? So frequency is the number of occurrence for each outcome. By the way, earlier I said my view is called the frequentist approach. So we call them frequentists because their view of probability is based on frequencies. So counting frequency is probability, right? So this is simply summary of the data. This summary doesn't lose any information, basically. So if you are wondering the order, otherwise, like what I only lose is the order. I observe 1 from the first experiment, 5 from the second experiment, but you don't need that information, right? Other than that, I contain all the information, but still I could summarize the information a lot. It's much more compact. And then you know how to calculate the probability based on the frequency, right? Just ratio, proportion between frequency to the sample size. So out of 200 observations, I observe outcome 1 33 times. So their frequency is 16.5%. That is how we define probability based on the frequentist approach, right? I'm going to use this throughout this course. So then you can try this. So in this data, I calculated the probability. Then can you calculate the probability of even number? Like among these 6 outcomes, you know what are even numbers. Then try to calculate the probability of probability that you have an even number as an outcome. So I will show you this kind of questions a lot in between lectures. So like you can do it by yourself. Like you can use calculator and think about this question. They are important to follow and to understand what I do in the lecture. Okay, if you need more time, stop the video now and resume when you finish your calculation. I believe this is super simple. So even numbers are 2, 4, 6. So the probability of them are sum of these three probabilities, right? So, and the answer is 53.5%, right? This is, you know how to do it. It's easy. But what I want to tell you here is this table loses no information. This table contains all the probability information about dice. And based on the information, you can like manipulate the information and obtain another probability. That we do this a lot. So in many cases, I don't like this frequency distribution is still very complicated, not easy to present itself. In that case, we need to summarize even more by choosing the important event or an important measure. Like this, if you are interested only in even numbers, you may manipulate the probability distribution table and give present another probability. That is what we are going to do in the next video, right? Okay, and before finishing this video, I'd like to digress a little. It's a simple thing. So probability, in this course and in any textbook or any course uses either one of the three methods. 20% is basically same thing as 0.2 or 2/10. So if I say probability is 20% or probability is 0.2, probability is 2/10, that's basically the same thing. They are the same thing. However, I do not recommend you to use, so percentage is maybe the most common way to say to describe probability, but I don't recommend this because when you do algebra, it may confuse you. Percentage basically means you multiply 100 to this decimal, right? Say 20%, 30%. If you multiply them, they are not 600%. You have to do this way. So 20% is 0.2, 300% is 0.3. So if you multiply them, you get 0.06. So it's 6%, not 600%. So it is pretty confusing. So I recommend you use either fraction or decimal. Like percentage is dangerous in algebra. Okay. So and finally, I will summarize what we are going to do. Probability is defined on an event. I define event is the target of a probability, right? So the probability doesn't need to be a single outcome, as you could see in our previous question. So event can be, you can define probability for even numbers. Like I can think about probability for 1 or 2. That's a single outcome. But you can think about probability that for an event that the outcome is smaller than 5, for example. You can define the probability. So technically, mathematically, the target of probability is not an outcome because you can do more general probability, right? So event is a set of outcomes where a probability can be defined. So mathematically, outcome is just one single outcome, but you can think of probability as a collection of outcomes. For example, single outcome can be an event, or any set of multiple outcomes can be an event. Or you can think about an empty set, empty event. So an event that does not include any possible outcomes has probability 0. For example, what is the probability that an outcome is a negative number? 0%. So there's nothing wrong. The probability is 0, and you may define an event that does not include any possible outcome. So event does not need to be an outcome, and an event may include all possible outcomes, like probability of a natural number or probability of integers, right? So not a big problem. Oh, fire alarm rings. Okay, this is it. So I will see you in the next video.